Atoms are the building blocks of our universe. They are incredibly small, yet they contain even tinier particles called electrons. These electrons are not just tiny balls of matter orbiting the nucleus like planets around a star. Quantum mechanics, the theory that governs the subatomic world, tells us something far more intriguing. Electrons behave like waves and particles simultaneously, a concept known as wave-particle duality. Instead of fixed orbits, they exist in fuzzy clouds of probability called orbitals. These orbitals determine the electron's energy level and the likelihood of finding it at a particular location around the nucleus. The traditional periodic table arranges elements based on their atomic number, which represents the number of protons in an atom's nucleus. This arrangement reflects recurring chemical properties, but it doesn't fully capture the dynamic nature of electrons and their intricate dance within the atom. To delve deeper into the mysteries of matter, we must explore the fascinating world of quantum wave functions and their potential connection to a fascinating concept, quantum fractals. Imagine listening to a symphony orchestra. Each instrument plays a unique note, and together they create a harmonious blend of sound. Similarly, electrons within an atom vibrate with specific frequencies, creating a symphony of their own. These frequencies are described by mathematical functions called wave functions. Just as musical notes can be represented visually on a musical score, electron wave functions can be plotted in three-dimensional space. These plots reveal intricate patterns that resemble complex, self-similar structures known as fractals. Fractals are geometric shapes that exhibit self-similarity, meaning they are made up of smaller copies of themselves at different scales. Think of a tree. Its branches resemble smaller versions of the trunk, and the twigs resemble even smaller branches. This repeating pattern is characteristic of fractals. The fractal-like nature of electron orbitals suggests a hidden order within the atom, a symphony of vibrations governed by the principles of quantum mechanics. This intriguing connection between the subatomic world and the realm of fractals has fascinated scientists and artists alike, prompting further exploration into the profound implications of this connection. In the early 20th century, an artist and polymath named Walter Russell proposed a radical new way of understanding the elements. Russell believed that the universe was governed by a fundamental principle of rhythmic cyclical motion, which he called the law of octaves. He developed a unique, spiral-shaped periodic table that arranged the elements not just by atomic number, but also by their vibrational frequencies, which he believed followed an octave-based pattern. This arrangement suggested that elements were not isolated entities but rather expressions of a continuous spectrum of energy. Russell's ideas were met with skepticism from the scientific community, as they lacked experimental verification at the time. However, his work has recently experienced a resurgence of interest, particularly among those exploring the intersection of quantum mechanics, fractal geometry, and the nature of consciousness. While Russell's theories remain outside the mainstream, they offer a tantalizing glimpse into a possible deeper order within the elements, one that resonates with the emerging understanding of the quantum world. Section 4. Harmonies of the Universe, Connecting Octaves and Quantum Waves. Could there be a connection between Walter Russell's octave-based system and the wave functions that describe electron behavior? This is a question that has sparked debate and curiosity among scientists and philosophers alike. Quantum mechanics reveals that electrons can only exist at specific energy levels like musical notes on a scale. These energy levels are quantized, meaning they are discrete and not continuous. It is intriguing to consider whether these quantized energy levels might correspond to the octave intervals proposed by Russell. Furthermore, just as musical harmonics create richer and more complex sounds, could electron wave functions also exhibit harmonic relationships? Could these harmonics contribute to the unique properties of each element and their interactions with one another? While the connection between Russell's octaves and quantum wave function harmonics remains speculative, it presents a compelling avenue for further investigation. Exploring this potential link could unlock a deeper understanding of the fundamental nature of matter and its connection to the underlying fabric of the cosmos. Section 5. The Quantum Orchestra, Entanglement and Superposition in Element Formation. Quantum entanglement and superposition are two of the most mind-boggling concepts in quantum mechanics, yet they play a crucial role in the formation of elements. Entanglement describes a state where two or more particles become linked, even when separated by vast distances. Their fates are intertwined, and measuring the state of one particle instantly influences the state of the others. Superposition, on the other hand, allows particles to exist in multiple states simultaneously until measured. Imagine a coin spinning in the air. It is neither heads nor tails until it lands. Similarly, an electron in superposition exists in a blurry combination of all possible states, defying our classical intuition. In the extreme environments of stars and other high-energy cosmic events, entanglement and superposition become even more pronounced. These quantum phenomena likely influence the very processes that forge elements within these cosmic furnaces. For instance, during nuclear fusion, atomic nuclei collide and fuse, creating heavier elements. Entanglement and superposition could play a crucial role in these reactions, affecting the probability of different fusion outcomes and influencing the abundance of elements in the universe. Section 6. Forging elements in the cosmic fire plasma as a quantum playground. Plasma, often called the fourth state of matter, is a superheated ionized gas where atoms have been stripped of some or all of their electrons. Stars, including our sun, are giant balls of plasma, and it is within these fiery cauldrons that most of the elements in the universe are created. Plasma is a chaotic and energetic environment where quantum effects reign supreme. The high temperatures and densities create a seething soup of particles constantly colliding and interacting. In this extreme environment, the wave-like nature of matter becomes even more pronounced, and quantum entanglement and superposition likely play a significant role in the formation of elements. Imagine the plasma within a star as a vast quantum orchestra. The electrons, protons, and neutrons are the musicians, and the forces between them are the conductor's baton. As the temperature and pressure rise, the orchestra plays faster and with greater intensity, creating a symphony of nuclear reactions that forge heavier and heavier elements. Understanding the interplay between plasma physics and quantum mechanics is crucial to unraveling the mysteries of element formation and the evolution of the universe itself.